Hello everyone, welcome to Adam. So now we are going to solve this question based on ideal cycle, where we have been given the initial conditions and the compression ratio and the heat supplied, and we have been asked to calculate the cutoff ratio, the cycle efficiency, and the work done per unit mass of the air. So let us see how we can solve this question. So firstly, if we draw the typical diagram for a D2 cycle, we have something like this: 1, 2, 3, 4, AV. We have process 1 to 2 as the isentropic compression process. Process 2 to 3 is the heat addition process, and 4 to 1 is the heat rejection process, and 3 to 4 is where the work is done by the engine on the piston and to the crankshaft. So heat addition process will be a constant pressure process, which is the Q supplied, because it is a diesel cycle. In the Otto cycle, it should be a constant volume heat addition process. So this is how you can draw a typical diesel cycle diagram. Next thing we have is we need to calculate firstly the cutoff ratio. So what is cutoff ratio? Cutoff ratio is nothing but the uh, ratio of volume after combustion divided by volume before combustion. In our case, it will be V3 divided by V2, which can be also written as T3 by T. So let's see how we can write V3 by V2 as T3 by T2, because 2 to 3 is a constant pressure process. So P will be equal to RT by V because of ideal gas equation. So if you say that this pressure should be constant, then you say that T2 by V2 should be equal to T3 by V3, which means that V3 by V2 should be equal to T3 divided by T2. So from this, you can say that V3 by V2, which is the cutoff pressure, should be equal to T3 by T2 also. So we need to find the temperature at point 2 and temperature at point 3 now. So because it is already given the temperature at point 1, so we will deal with temperature only, because it will be easy for us to do. So we have T1 as 40 degrees Celsius, which if you convert it into like Kelvin, you have 273 plus 40, it's equal to 313 Kelvin. You have a pressure at point 1 as zero point 0.1 megapascal. Oh yeah. So we have isentropic compression between process 1 to 2, which is PV to the power gamma should be equal to constant. Pressure at point. So if you apply this as between 1 to 2, we have P1, V1 to the power gamma should be equal to P2, V2 to the power gamma. And but we need to convert this into a temperature and volume terms, because we know the compression ratio and we know the temperature at point 1 also. So you can just substitute P as RT by V here. You'll get something as T1, V1 to the power gamma minus should be equal to T2, V2 to the power gamma minus 1. And you can easily find T2 from here, which will be T1, T2, V1 by V2 to the power gamma minus 1. And V1 by V2 is nothing but V1 will be volume before compression, and V2 will be this volume, which is volume at point 2, which is a volume after compression. And the ratio of volume before compression divided by volume after compression will be nothing but the compression ratio. So we have a T1 as 330 Kelvin, V1 by V2 as 80, gamma minus 1 as 0.4. So if you calculate this, you will get something as a 994.6 Kelvin. So this is your T2. So you can just write it here like T2 is nothing but 994.6 Kelvin. If you would like have found the value of T2, you can now need to find the value of T3 to calculate the cutoff ratio. So let's see how we can do that. So we have a constant pressure heat addition and between the process of 2 to 3, which we have been given in the question as 1500 kilojoule per kg heat is supplied between process 2 to 3, which can be written as Cp into delta T per unit kilojoule of kg per unit kg of the air. So Cp delta T should be become 1500, because this is nothing but the heat supplied at constant pressure because of Cp, and this is given in the question. So if you just equate this for the value of air, we have 1.005 as the value of Cp, kilojoule per kg Kelvin, into delta T will be T3 minus T2. It should be equal to 1500 from the question. This is also in the kilojoule per kg. And this value is for air. Cp value for the air. So if it would have been a constant volume like heat addition process such as an Otto cycle, so you have to write Cv in place of Cp. You will get the total heat supplied per kg of the fuel using Cv delta T, not Cp delta T, if it would have been a constant volume process. But in our case, it is a diesel cycle, so we have Cp delta T as the heat supplied per unit kg of the air. So you can just calculate the value of T3 from here. T3 will be 2487.13 Kelvin. So you can just write T3 as 2487.13 Kelvin. So after we have calculated T3, you can just easily say that the cutoff ratio, which is nothing but V3 by V2, will be T3 by T2, and this we have found out to be 2487.13 divided by 994.6, and this should be equal to 2.5, which is equal to alpha. So we have calculated alpha as 2.5, which is our cutoff ratio. So first step of the question, or the first part of the question, we have shown as for the cutoff ratio. And the next thing we have been asked is the cycle efficiency. So cycle efficiency formula, if you know for the diesel cycle, it will be very easy for you to solve. We have 1 minus 1 divided by r to the power of minus 1 into alpha to the power of minus 1 divided by gamma into alpha minus 1. And alpha here is the cutoff ratio, gamma is the isentropic coefficient, and the r is the compression ratio. So if you just put the values which we have, which is nothing but 18 to the power 0.4 into alpha, which is 2.5 to the power 1.4 minus 1 divided by 1.4 into 1.5, which is alpha minus 1. And because alpha is 2.5. So you will get efficiency something as a 60.93% if you calculate this from this equation. And next thing we have been asked is the work done per unit mass of the air. And if you know that efficiency is nothing but the work done divided by heat supplied. So you can easily calculate the work done from here, because we have been given the heat supplied in the question and we don't know the efficiency now. So work done becomes efficiency into heat supplied, which is 1500 kilojoule per kg given in the question, into 60.93%. So it should become 940 kilojoule per kg of heat supplied. Of work done. So this is how you can solve all the three parts of the question. Thank you.